What if the greatest event in the history of the universe after its own birth happened in absolute perfect darkness? Not the familiar dark of a country night punctuated by stars, but a profound, suffocating blackness, an abyss that swallowed light before it could even begin its journey. You're living in the aftermath of that event. Every star you see, every galaxy our telescopes unveil, every photon of ancient light that strikes your eye is a testament to a victory won in that primordial night. When you gaze into the cosmos today, you're looking into a crystal palace. It is a space of almost impossible transparency, a void so clear that we can witness galaxies burning at the edge of time, their light having travelled for over 13 billion years to reach us. We see the grand cosmic web, a luminous scaffold of galactic superclusters strung together by filaments of dark matter and incandescent gas. We see stellar nurseries glowing with the rose-pink light of ionized hydrogen, birthing new suns in spectacular displays of celestial pyrotechnics. We see the ghosts of dead stars and the violent hearts of quasars' celestial blowtorches outshining their entire host galaxies. This universe is alive with a light structure and story. It is a complex, interconnected and fundamentally visible reality. And yet this breathtaking clarity, this permission to see, is a recent privilege. For the first few 100 million years of its existence, the universe you know did not exist. Imagine rewinding time past the dinosaurs, past the formation of Earth, past the birth of the Milky Way itself. You push further and further back into an epoch so remote it defies all human scales of comprehension. Here in the tender infancy of creation, the universe was a different beast entirely. It was a place of utter crushing uniformity. There were no galaxies to cluster, no stars to ignite the void. There was only a vast expanding and cooling sea of hydrogen and helium gas, a cosmic fog that permeated everything everywhere. This was not an empty darkness. It was a full darkness, a darkness with substance. The universe was shrouded in a primordial cataract of its own making. Every atom of hydrogen, the most abundant element forged in the Big Bang, existed in its neutral state, a single proton orbited by a single electron. And this seemingly innocent configuration was the perfect cosmic cage for light. Any flicker of ultraviolet radiation, the very lifeblood of a young star, would travel no further than its immediate neighbourhood, before being greedily absorbed by a neutral hydrogen atom. Light was trapped, imprisoned on a subatomic scale. The cosmos was opaque. An observer inside this fog would have seen nothing but an impenetrable wall of grey, a universal whiteout stretching to infinity in all directions. This was the great cosmic dark age. It was a silent waiting period in the universe's biography, a long and patient inhalation before the first great shout of existence. For nearly 400,000 years after the Big Bang, the universe had been a searing, brilliant plasma, a particle soup so hot that atoms could not form. Light and matter were locked in an inseparable dance. Then, as expansion cooled this cosmic furnace, a critical threshold was crossed. Protons and electrons, once frenetically unbound, could finally embrace each other to form the first neutral atoms. This moment, known as recombination, is ironically the instant the universe went dark. The light from that primordial fireball was set free for the last time, becoming the faint cosmic microwave background radiation we detect today. But in its wake, it left a universe filled with that light-trapping hydrogen gas. The stage was set, but the theatre was dark. The script was written in the language of gravity, which worked tirelessly and silently in the gloom. Subtle fluctuations in density, infinitesimally small variations imprinted on the cosmos in its first moments, became the seeds of everything that was to come. Gravity. The quiet architect began to pull matter toward these denser regions. Slowly, patiently, over millions of years, wisps of hydrogen began to coalesce. The fog began to curdle. What started as slight overdensities grew into vast rotating clouds of gas-titanic structures, dwarfing anything we know today. They were the proto-galaxies, the sleeping giants of the early cosmos, and within their cold, dark hearts, pressure was building. For 100 million years, then 200, then perhaps 400 million, this silent gravitational assembly continued. It was the longest period of gestation imaginable, the universe gathering its strength, concentrating its potential, preparing for its own violent birth into visibility. Something had to break the spell. Something had to rise up from within that infinite darkness and tear the veil of hydrogen apart atom by atom. Something had to turn the lights on. That something ignited a revolution, a transformation so profound it has no parallel. It is an event we call the Epoch of Reionization. The name itself hints at the deep physics of the story. The universe, which was once ionized in the Big Bang's heat, and then became neutral during the Dark Ages, had to be ionized again. But this time the energy would not come from the residual heat of creation. It would come from within. It would be the fierce, brutal and glorious light of the very first stars. Deep inside those collapsing clouds of primordial gas, the cores reached temperatures and pressures unseen since the Big Bang. Nuclear fusion ignited. The first suns were born, and they were not like our gentle, stable star. Cosmological models and theoretical physics paint a terrifying picture of these pioneers. They were monsters of pure hydrogen and helium, hundreds, perhaps even thousands of times more massive than our Sun. Because of this immense mass, they burned with an unimaginable ferocity, blazing with a luminosity millions of times greater than stars today. They were short-lived titans, celestial blast furnaces that lived fast and died young in supernova explosions of apocalyptic scale. But during their brief, spectacular lives, they unleashed a torrent of high-energy ultraviolet radiation, a relentless barrage of photons with enough power to shatter the tranquil neutrality of the surrounding hydrogen gas. This was the weapon that would win the war against the darkness. When one of these powerful photons struck a neutral hydrogen atom, it didn't just nudge it. It violently kicked the electron away from its proton, splitting the atom back into its charged ionized components. An ionized atom of hydrogen is a ghost to light. It can no longer absorb those energetic photons. In that one tiny violent interaction, a minuscule volume of the universe suddenly became transparent. Now imagine this process multiplied by billions. The first star ignites and a bubble of clarity expands around it, a sphere of newly ionized transparent space carved out of the cosmic fog. Inside this bubble, light can finally travel freely, but the moment that star dies, its bubble of influence begins to shrink as the hydrogen atoms recapture their lost electrons and the fog closes back in. It was not a war that could be won by a single soldier. An army was needed. As more and more of these population 3 stars, as we call them, blazed into existence within the first proto-galaxies, their individual bubbles of transparency began to grow. They expanded outwards like rising balloons' frontiers of light pushing back the frontiers of darkness. Where 2 bubbles met, they merged, creating ever larger, more complex zones of visibility. For hundreds of millions of years, the universe was a chaotic, frothy battleground. It was a cosmic civil war fought between radiation and matter. Pockets of the cosmos would flicker into transparency, only to be plunged back into obscurity. Entire regions, vast beyond imagination, would be cleared of the fog, while neighbouring voids remained stubbornly opaque. It was a messy, piecemeal and protracted affair. The universe did not simply wake up at once. It was roused from its slumber region, galaxy by galaxy, in a staggering transition that we're only now beginning to comprehend. The process was likely accelerated by the emergence of other cosmic engines. The first quasars, supermassive black holes feeding ferociously at the centres of galaxies, would have unleashed beams of radiation far more powerful than any single star or even a cluster of stars. These were the heavy artillery in the war for light capable of ionizing enormous swathes of the intergalactic medium in a single blast. Slowly, inexorably, the balance of power shifted. The forces of ionization driven by the first generation of cosmic objects gained the upper hand. The isolated bubbles of transparency linked up, forming vast networks, then continents of clarity, until finally the last vestiges of the neutral fog evaporated. The great clearing was complete. The intergalactic medium, the vast space between the galaxies, was left a tenuous, searingly hot, and almost entirely transparent plasma. Light, for the first time since the moments after the Big Bang, was a traveller, not a prisoner. The universe had achieved its luminous adulthood. The stage was now fully lit, revealing the grand drama of cosmic evolution that would lead directly to the formation of our own Milky Way, our Sun, and ultimately to us. Our ability to do astronomy, our very perception of the cosmos, is predicated on the successful outcome of this ancient struggle. Without reionization, the universe would remain a place of isolated islands of light, each one ignorant of the other's existence, separated by an eternal and impenetrable fog. We would be blind. This monumental transformation, the most important event since the cooling of the Big Bang's fireball, is now one of the greatest unsolved puzzles in modern cosmology. It represents a frontier in our understanding, a dark chapter in the cosmic story that we are desperately trying to illuminate. The central questions are as profound as they are challenging. What exactly were the first objects that ignited this process? Were they truly those monstrous ephemeral stars, or did the first ravenous black holes play a more significant role than we suspect? How did such a sparse population of infant galaxies, mere seeds of the giants we see today, manage to collectively transform every cubic light-year of the observable universe? The sheer scale of the energy required is difficult to fathom. It was a global change driven by local actors, and understanding that incredible feedback loop is the key. Was the process a slow, gentle sunrise? Or was it a violent, flickering storm of radiation with dramatic advances and retreats? And perhaps most tantalizingly, what signatures of this epic battle can we still detect today? Are there faint echoes of this epoch imprinted on the light of distant quasars? Can we find fossil evidence in the distribution of the oldest galaxies? Answering these questions is not merely an academic exercise. It is a journey to uncover our own ultimate origins. To understand Reionization is to understand the moment our universe became the universe we recognize. It is the search for the first dawn, for the precise instant, give or take a few 100 million years, when the cosmos truly opened its eyes. And now, with a new generation of powerful telescopes instruments designed to capture the faintest and most ancient light, we are finally building the time machines capable of taking us there. We are pushing past the familiar galaxies, peering deeper into the abyss of time, searching for the faint stretched-out light from those very first cosmic revolutionaries. We are on the cusp of witnessing the end of the Dark Ages and the beginning of everything else. The story of creation is not over. We are just now learning how to read its earliest, most dramatic chapter. What if the most profound event in cosmic history was not a sound, but a silence? Not a bang, but the long drawn-out moment after the echo finally faded. We have just witnessed the universe's fiery birth announcement, the afterglow of creation itself, painted across the entire sky as the cosmic microwave background. A flash of primordial radiation released at the very instant the cosmos became transparent for the first time. For 380,000 years it was a searing inferno of plasma, a particle storm where light was trapped in an endless game of pinball. Then, in a moment of cosmic alchemy, the storm broke. The universe cooled just enough for the frantic dance to end, for protons to finally capture electrons, forming the first stable atoms. This was the moment of recombination, the great decoupling of matter and light. And with it came that first glorious universe-spanning burst of freedom for photons. You would think this was the beginning of illumination. You would be wrong. This was the moment the lights went out. The universe, having finally unshackled light from matter, immediately drew a new curtain across the stage. A curtain made of the very atoms it had just created. It plunged itself into a profound, starless, galaxyless twilight that would last for hundreds of millions of years. This was not the darkness of a familiar night sky punctuated by the distant reassurance of stars. This was an absolute featureless and oppressive blackness. Welcome to the cosmic dark ages. Imagine yourself adrift in this nascent cosmos. There is no up or down, no east or west. There are no landmarks, no celestial bodies to orient by. There is only you and an endless uniform ocean of hydrogen and helium gas, extending in every direction forever. This isn't an empty void. The universe is denser now than it will ever be again. It's a thick, pervasive fog of neutral atoms. The word neutral is the key to this entire epoch. In the plasma that came before electrons and protons were separate charged particles scattering light like beads of water in a dense cloud. Now bound together into atoms of hydrogen, they have become electrically neutral. This new state has a powerful counterintuitive effect on light. While the searing high-energy light of the Big Bang's afterglow could pass through this new medium, any new light, any lower-energy visible light that might hypothetically be generated would be instantly smothered. A neutral hydrogen atom is a perfect trap for photons of specific energies. It absorbs them, holds them, and prevents them from travelling. So even if a source of light could magically appear, its rays would travel no farther than a candle's flicker in a London fog. The universe had become opaque again, but in a new, more subtle way. It had traded a prison of hot plasma for a smothering blanket of cold gas. The grand intermission of the cosmos had begun. For an almost unimaginable stretch of time, nothing truly happened. The universe was simply expanding and cooling. The temperature once measured in billions of degrees was now dropping steadily. From thousands of degrees at the start of this era, it fell to hundreds, and then after millions of years to a frigid 270 degrees below 0 Celsius, just a few degrees above absolute zero. It was a universe in hibernation, a kingdom of atomic simplicity. Over 90% of the matter you could touch was hydrogen, a single proton orbited by a single electron. The rest was mostly helium with trace amounts of lithium, the only elements forged in the furnace of the Big Bang. There were no heavier elements, no carbon for life, no oxygen to breathe, no silicon for rocks, or iron for a planet's core. The chemical richness that makes our world possible was not even a distant dream. The cosmic recipe was stark and elemental. The ingredients for everything we know existed, but they were unassembled, floating in a diffuse silent sea. The only force that held any sway over this immense quiet was gravity, and gravity is patient. Yet this primordial ocean was not perfectly smooth. The afterglow of the Big Bang, the cosmic microwave background, shows us that. It contains minuscule temperature fluctuations, tiny imperfections in the otherwise uniform fabric of the early universe. These are the fossilized echoes of quantum jitters from the very first moments of time expanded to astrophysical scales. In the cosmic dark ages, these irregularities correspond to regions where the gas is infinitesimally denser than the surrounding regions, a millionth of a percent denser. The difference is so small it's almost laughable. Imagine a billiard ball the size of the Earth. These imperfections would be smaller than a single human cell, and yet within these microscopic seeds of structure lay the blueprint for the entire future of the cosmos. For gravity, however weak, is relentless. It began its silent, painstaking work. In a region that was just 1/1,000,000th more dense, there was 1/1,000,000th more gravitational pull. Over 1,000,000 years, that tiny advantage would draw in a whisper more of the surrounding gas. Over 10 million years, that whisper would become a murmur. Over 50 million years, a slow, inexorable current. The rich were getting richer. We are witnessing the birth of the cosmic web not in a flash of light, but in the slow, invisible gathering of darkness. The architects of this construction were not the atoms of hydrogen and helium themselves. They were merely the building materials. The true sculptors were something else entirely, something invisible, something that had been present since the beginning, but had largely remained aloof from the chaos of the plasma era. We call it dark matter. This mysterious, unseen substance makes up over 80% of the matter in the universe. It does not interact with light. It does not feel the electromagnetic force. It is a ghost in the cosmic machine perceptible only through its immense gravitational influence. During the fiery plasma age, when normal matter was being pushed around by the pressure of radiation, dark matter was already calmly and quietly succumbing to gravity. It had a head start. By the time the Dark Ages began, it had already started to form vast invisible structures, a web of immense filaments and dense spherical halos stretching across the cosmos. It was creating the gravitational scaffolding, the cosmic riverbeds into which the normal matter, the hydrogen and helium gas, could now begin to flow. So picture the scene. Across billions of light years, a ghostly invisible skeleton of dark matter is taking shape. And into these great unseen valleys and basins, the primordial gas of the universe begins to drain. The process is agonizingly slow. For 100 million years, the change is almost imperceptible. The universe remains dark, cold, and almost entirely uniform. The gas clouds, even as they slowly contract, are not dense enough, not hot enough to do anything. They are simply collapsing under their own weight, a process that will take eons, But here inside the densest knots of the dark matter web within the deepest gravitational wells, something is beginning to stir. The gas is becoming more and more compressed. The atoms once spread far apart are now being crushed together. The gravitational potential energy of the collapse is slowly, steadily being converted into heat. In the very centre of the most massive dark matter halos, the temperature of the hydrogen gas begins to climb, from a frigid 200 below zero to 100 below to zero. For the first time since the Big Bang's afterglow faded, pockets of the universe are starting to heat up. The pressure is building. We are approaching a tipping point. We are approaching the moment when the long cosmic night is about to break. Our only window into this lost era is a whisper, a faint, almost imperceptible radio signal with a wavelength of 21 centimeters. This is the signature of neutral hydrogen itself. Occasionally, the electron in a hydrogen atom will spontaneously flip its spin relative to the proton it orbits. When it does, it releases a tiny puff of energy, a single photon with this exact wavelength. It is an incredibly rare event for any individual atom, but in a universe filled with an almost infinite number of them, it was happening everywhere all the time. This faint universe-spanning hum is the only direct evidence we have from the Dark Ages. By studying its faint variations across the sky, astronomers are trying to map the ghostly structures of this primordial time. They are searching for the telltale signs of the first great gas clouds collapsing, listening for the soundtrack of the universe just before the dawn. It is cosmic archaeology on the grandest scale, sifting through the oldest static in creation to find the story of our own origins. We can see the clouds gathering. We can detect the gravitational collapse. We can measure the slow rise in temperature in these nascent cocoons of matter. Everything is in place. The stage is set for the most dramatic transformation the universe has ever undergone. Inside these collapsing clouds, these protogalaxies, the density and temperature are reaching critical thresholds. A point is coming where the relentless crush of gravity will overwhelm the outward pressure of the gas. A point where the hydrogen atoms will be squeezed so tightly that their nuclei will be forced to touch, to fuse, to ignite in a furious burst of thermonuclear energy. The first sparks are about to fly in the cosmic dark. The universe has spent hundreds of millions of years assembling the fuel, creating the conditions and building the engines. It has built the pyres. Now it needs a match. But this raises the ultimate question of this epoch. The transition from the Dark Ages to an illuminated cosmos is not a gentle one. It is not about a few lights winking on here and there. To end the darkness, the universe must be utterly and violently transformed. The very fabric of the cosmos, that thick, light-absorbing fog of neutral hydrogen, has to be systematically and completely destroyed. Every single hydrogen atom in every cloud, in every filament across the entire observable universe must be ripped apart. The electron must be stripped away from its proton, turning the gas back into the charged plasma it once was. This process is called reionization. It requires a staggering, almost incomprehensible amount of energy. Enough energy to ionize 100 billion galaxies worth of hydrogen. Enough energy to burn away the primordial fog and make the entire universe transparent to light once and for all. Gravity, for all its power, cannot do this. The slow collapse of gas can't do this. The heat from compression is not nearly enough. The universe requires a new force, a new kind of energy source, more violent and more powerful than anything that has existed since the Big Bang itself. It needs celestial blowtorches, billions of them blazing with the fury of 1 trillion suns to blast through the cosmic gloom and end the long night. The mystery of the Dark Ages, then, is not that it was dark. The mystery is how it ever ended. What was this new power? What were these first ferocious engines of creation born in the heart of the primordial darkness that were powerful enough to set the entire universe on fire? For an eternity measured in silence, gravity was the universe's only active force, a patient and invisible sculptor working in absolute darkness. Within the vast cold clouds of hydrogen and helium that filled all of space, the subtlest of quantum fluctuations imprinted at the dawn of time had grown into regions of infinitesimally higher density. Here in these unseen cosmic shallows, the pull was just a little stronger. For millions of years, this silent, inexorable gathering was the only story. Atoms drawn by a force they could not resist began to fall toward common centers. their random thermal dance slowly giving way to a collective inward spiral. The universe was holding its breath, waiting for a spark. But where would that spark come from? How could light ever arise from a cosmos made of nothing but cold, dark gas? The answer for decades existed only in the realm of pure thought, in the complex architecture of supercomputer simulations. Long before our telescopes could ever hope to glimpse it, we had to first imagine it. We had to build a virtual universe and watch it evolve frame by painstaking frame until the first lights turned on. These simulations became our theoretical time machines, allowing us to witness the birth of objects that no longer exist, a generation of titans that lived and died before the cosmos was even 1 billion years old. We call them Population 3 stars. The name is a historical quirk, a classification that belies their true significance, for they were not third but utterly irreducibly first. They were forged from the universe's raw ingredients, pristine hydrogen and helium, untouched by the alchemy of any prior stellar furnace. And this purity, this lack of heavier elements, was the secret to both their majesty and their tragedy. In the star-forming clouds of our modern galaxy, elements like carbon and oxygen act as coolants, radiating away heat and allowing gas to fragment into countless smaller, more stable clumps. This is why our Sun is a relatively modest star, one among billions. But in that primordial gas, there were no such coolants. The collapsing clouds of hydrogen could not easily shed their heat. They couldn't shatter into 1,000 stellar embers. Instead, they collapsed monolithically, piling on mass, in a gravitational runaway growing to proportions that stagger the modern imagination. These were not stars as we know them, they were cosmic behemoths. Our simulations predict Population 3 stars swelling to 100, 200, perhaps even 500 times the mass of our own Sun. They were not the familiar yellow-white of our star, but searing, brilliant blue-white points of impossible heat, burning their nuclear fuel with a suicidal fury. Their surface temperatures would have reached over 100,000 degrees, unleashing torrents of high-energy ultraviolet radiation into the surrounding darkness. A Population 3 star was a celestial blowtorch, a lonely titan raging against the eternal night. And because they burned so violently, they lived fast and died young. While our Sun is destined for a lifespan of 10 billion years, these first stars would have exhausted their fuel in a mere 1 or 2 million years, a fleeting instant on the cosmic timescale. Their end would have been as spectacular as their existence. Not a gentle fading, but a cataclysmic supernova, of a kind we no longer see an explosion so powerful it would have momentarily outshined all the other stars in its nascent galaxy combined. In their final violent moments, these stars performed the single, most important act of creation since the Big Bang itself. Within their collapsing cores under pressures and temperatures beyond comprehension, hydrogen and helium were finally fused into heavier elements: carbon, oxygen, silicon, iron. For the very first time, the universe was seasoned with the ingredients necessary for planets for life for us. With their dying breaths, the Population 3 stars seeded the cosmos, their elemental ashes blasted across space to be incorporated into the next generation of stars, Population 2. Without their sacrifice, the universe might have remained a sterile, simple place, forever composed of only the 2 lightest gases. They were the bridge between the simplicity of the beginning and the complexity we see today. But these stellar titans were not born in isolation. They would have ignited within the deepest gravitational wells the densest knots of the invisible web of dark matter that provided the universe's underlying scaffolding. These regions were the first true cosmic structures, the seeds of what would one day become galaxies. Imagine these proto-galaxies. They were not the grand, elegant spirals we see through our telescopes today. They were chaotic, messy, brilliant congregations of gas, and the first few generations of stars all churning within a halo of dark matter. Thousands, perhaps millions of times smaller than our Milky Way, they were nevertheless the first beacons in the void, the first cities of light in an otherwise uninhabited wilderness. Within them, stars were being born at a furious rate, each one contributing its own sphere of influence, its own bubble of radiation pushing back against the encroaching dark. And at the very heart of these primordial cities, an even more ferocious monster was stirring. The remnants of the most massive population 3 stars, instead of exploding completely, may have collapsed directly into black holes hundreds of times the mass of our Sun. In the dense gas-rich environment of a protogalaxy's core, these seed black holes would have found a feast. Gas stars and other black holes all spiralling inward would have merged and been consumed in a gravitational vortex of unimaginable power. This process gave birth to a new kind of cosmic engine, an object whose luminosity defies belief: the quasar. A quasar is not a star. It is the incandescent fury of matter being torn apart as it spirals into a supermassive black hole. As gas is pulled into the black hole's accretion disk, it is compressed and heated to millions of degrees, unleashing a torrent of energy across the entire electromagnetic spectrum, a cosmic searchlight that can outshine its entire host galaxy by a factor of thousands. The very first quasars powered by the first supermassive black holes would have been the most luminous single objects in the early universe. Their light, a piercing beacon of X-rays and ultraviolet radiation, was a weapon capable of carving vast tunnels of transparency through the neutral hydrogen fog on a scale that dwarfed even the most powerful population 3 stars. The existence of these objects, these stellar titans and ravenous black holes, provided a powerful theoretical solution to the problem of the Dark Ages. They were the matches, the lighters, the cosmic flamethrowers capable of setting the universe alight. For a long time, this beautiful, violent story remained just that, a story told by the silent logic of computer code. The challenge was immense. How could we ever hope to find observational proof for a transition that happened over 13 billion years ago at the very edge of the visible universe? Finding direct evidence was like trying to solve a crime where the scene is on the other side of the world, shrouded in fog, and the only clues are faint ancient echoes. Astronomers knew they couldn't see the first stars directly. They were too faint, too distant, too long gone. They couldn't peer into the Dark Ages itself because by definition it was opaque. They needed a different strategy, an indirect method to probe the state of the universe during that crucial transitional period. They needed to find a way to see the darkness itself. The breakthrough came not from building a better telescope to see fainter, but by using the universe's brightest objects to see what was in between. The most distant quasars, those brilliant beacons from the dawn of time, offered the perfect tool. Their light has travelled for billions of years to reach us, and on that epic journey, it passes through the intervening cosmic ages, like a core sample drilled through geologic strata. The spectrum of that light, the rainbow of its constituent colours, carries an imprint, a detailed chemical fingerprint of everything it has encountered along the way. In 1965, 2 young astronomers, James Gunn and Bruce Peterson, proposed a thought experiment of profound elegance. They reasoned that if you looked at the light from a very distant quasar, you were essentially looking back through the Reionization Epoch and into the tail end of the Dark Ages. If that intervening space was filled with the vast diffuse clouds of neutral hydrogen gas, the very stuff of the primordial darkness, then that gas should leave a dramatic signature on the quasar's light. Neutral hydrogen is exceptionally good at absorbing photons of a very specific wavelength, 121.6 nanometers a line, in the ultraviolet part of the spectrum known as Lyman-alpha. As the light from the quasar travelled towards us, the expansion of the universe would stretch its wavelength. Light that began its journey as Lyman-alpha would be redshifted, but other shorter wavelength light would be stretched into the Lyman-alpha wavelength as it passed through gas clouds at different distances. Each cloud of neutral hydrogen along the line of sight would act like a tiny filter, taking a bite out of the quasar's spectrum at the wavelength corresponding to its distance. Looking at a quasar through a thin haze of neutral hydrogen would produce a forest of absorption lines, the Lyman-alpha forest, a well-known feature in the spectra of nearer quasars. But Gunn and Peterson's prediction was far more extreme. They asked what would happen if the quasar's light had to travel not through a few isolated clouds, but through a universe still fundamentally full of neutral hydrogen. A universe where the Dark Ages had not yet fully ended. In that case, there would be no isolated absorption lines. There would be no forest. There would be so much neutral hydrogen at every distance between us and the quasar that all the light below the Lyman-alpha wavelength would be absorbed. It wouldn't be a forest of lines. It would be a complete and total blackout. an impenetrable wall of absorption, an abyss in the spectrum. They called this predicted feature the Gunn-Peterson trough. For decades, this remained a purely theoretical prediction. Our telescopes simply weren't powerful enough, and we hadn't yet found quasars that were distant enough to be located on the far side of the Reionization event. We could see the Lyman-alpha forest evidence that the universe was largely cleared out and transparent, but we couldn't see the edge of the clearing. We couldn't find the wall of the old forest. Then at the dawn of the 21st century, a new generation of immense telescopes coupled with ambitious sky surveys began to push the frontier. Astronomers were finding quasars at ever greater distances, pushing back to when the universe was just a fraction of its current age. They were hunting for the edge. In 2001, a team using the Sloan Digital Sky Survey discovered a quasar at a redshift of 6.28. This meant its light had travelled for over 12.8 billion years to reach us. It was a messenger from a time when the cosmos was less than 1 billion years old. When they took a detailed spectrum of this object, they saw exactly what Gunn and Peterson had foreseen 36 years earlier. At the long wavelength end of the spectrum, the quasar's light shone brightly. But as they looked towards shorter, bluer wavelengths past the point corresponding to the quasar's own Lyman-alpha emission, the light simply vanished. The spectrum plunged into a deep, dark, flat-bottomed trough. There was nothing. It was an ethereal wall, a spectral abyss stretching across millions of light-years of cosmic history. This was the smoking gun. The discovery was one of the most profound moments in modern cosmology. That perfect, empty blackness in the spectrum was not an equipment failure. It was not a lack of signal. It was the signal itself. It was the positive detection of the primordial fog. The trough was the shadow cast by the last remnants of the cosmic dark ages, a definitive sign that at this early time the universe was still fundamentally opaque, saturated with the neutral hydrogen that had defined it for hundreds of millions of years. For the first time, we were not just inferring the existence of the dark epoch, we were seeing its direct, unambiguous effect on the cosmos. Other, even more distant quasars were found, and their spectra confirmed the finding. The Gunn-Peterson trough was real. It marked a cosmic boundary, a phase transition written in light. On one side of this boundary, the universe was transparent, the Lyman-alpha forest showing only the faint lingering wisps of gas. On the other side, the abyss, the evidence of a universe still struggling to emerge from its long twilight. We had found the culprits, the theoretical population 3 stars, and the nascent quasars powerful enough to ionize the cosmos. And now we had found the crime scene, the spectral evidence of the vast ocean of neutral gas they had to overcome. The pieces were finally on the board. The story was no longer just a simulation running on a computer, it was etched into the very light of the cosmos itself. The evidence told us that here at this epoch the great battle was underway. The first pinpricks of light born in the hearts of monstrous stars and at the edge of ravenous black holes were fighting a war against an ocean of darkness that spanned the entire universe. The existence of the Gunn-Peterson trough proved that at this point in history the darkness was still winning. But we know how the story ends. We live in a transparent universe filled with galaxies and light. So the question was no longer if the lights turned on, but how. How exactly did those first isolated islands of brilliance manage to conquer an entire cosmos? How did their individual bubbles of ionization grow, merge and ultimately overlap to burn away the primordial fog once and for all? For an eternity, it had been a story told only in the language of mathematics, a grand cosmic inference. We knew the fog of the Dark Ages must have lifted. Logic demanded a dawn. Our models of stellar evolution and galaxy formation painted vivid portraits of what this event, this great clearing, might have looked like. But these were elegant hypotheses, ghost stories whispered across 13 billion years of cosmic history. To turn theory into fact, to prove that a universe once shrouded in a neutral light-absorbing haze was forcibly rendered transparent, we needed more than equations. We needed evidence. We needed to become cosmic detectives searching for fingerprints left at a scene impossibly vast and ancient. The challenge was monumental. How do you find a smoking gun for an event that reshaped the entire observable universe? An event whose perpetrators had long since burned out, evolved or faded into the deep tapestry of space-time? The search would require two radically different strategies. One was a brute force approach, a direct hunt for the culprits themselves. The other, far more subtle, was a search for the scar the event left behind on the oldest light in existence. Our first line of inquiry demanded we build a time machine, not of gears and flashing lights, but of glass and mirrors and unimaginable patience. We needed to stare so deeply into space, so far back into the past, that we could catch a glimpse of the universe's very first cities of light. This was the profound promise of the Hubble Space Telescope. Suspended in the silent vacuum above the blurring distortions of Earth's atmosphere, Hubble was our single greatest eye on the cosmos. And its operators would embark on one of the most audacious gambles in the history of science. They would point this magnificent instrument at a minuscule, seemingly empty patch of the night sky, a region chosen specifically for its apparent lack of anything at all. It was a cosmic roll of the dice. If the theories were wrong, hundreds of hours of precious observing time, one of the most sought-after resources in all of science, would yield nothing but a dark, empty frame. But if they were right, that sliver of darkness held the faint treasured light of creation itself. This was the genesis of the Hubble Deep Field, and later, the ultra-deep and extreme deep fields. For days, weeks, accumulating hundreds of hours of exposure time, Hubble opened its shutter and simply waited. It drank in photons that had been travelling towards us since before the Earth had even formed, light that had journeyed across an expanding universe for over 12, then 13 billion years. And as the data trickled back to Earth frame by painstaking frame, the darkness began to give way. The empty patch of sky was not empty at all. It was teeming with life, not with creatures but with galaxies, thousands of them, each faint smudge of light a metropolis of stars. But these weren't the grand majestic spirals we see in our cosmic neighbourhood. The most distant objects in these portraits were different. They were small, chaotic, misshapen knots of furious blue and searing white light distorted and stretched by cosmic expansion into faint ghostly embers of infrared. This was it. We were looking at the universe's first generation of galactic architects. These were the prime suspects. Using the relentless physics of cosmic redshift, the process by which light from a receding object is stretched to longer, redder wavelengths, we could calculate their distance and therefore their age. The faintest, reddest specks in the Hubble images were galaxies shining when the universe was less than 1 billion years old, some dating back to just 500 or 600 million years after the Big Bang. We had found them, the lighters, the sources of the ionizing radiation that in theory had burned away the fog. The sheer number of them was staggering. Extrapolating from that tiny patch of sky to the entire cosmos implied a universe filled with billions, perhaps trillions of these nascent star-forming nurseries, each one a furnace of young, massive, intensely hot stars blazing with ultraviolet radiation. The images were a triumph, a vindication of the core idea. The culprits existed. But this discovery, as profound as it was, presented its own frustrating limitations. It was circumstantial evidence. Finding a lit match doesn't tell you precisely when a fire started, how long it burned, or if it was solely responsible for burning down the entire forest. We could see that the potential sources were there, but we couldn't definitively say, based on these images alone, that their combined output was sufficient to reionize the entire cosmos. Nor could we pinpoint when the process truly began and ended. The Hubble gave us the suspects, but we needed a different kind of clue to build a timeline of the event itself. We needed to find the echo of the fire, not just the embers. That echo cosmologists predicted would be imprinted on the most ancient artifact in our possession, the cosmic microwave background. The CMB, that faint pervasive afterglow of the Big Bang, is the universe's baby picture taken when it was just 380,000 years old. In the previous act, we understood it as a snapshot of the moment matter, and light decoupled when the primordial fog first cooled and cleared. But the story didn't end there. For hundreds of millions of years, that pristine light travelled through a universe that was transparent but filled with neutral hydrogen and helium gas. Then, as the first stars and galaxies ignited, their fierce radiation began to rip electrons from those neutral atoms, once more flooding the cosmos with a thin hot soup of free-floating charged particles. This is the crucial point. When the CMB light passed through this newly Reionized plasma, it would have interacted with those free electrons. The photons would have scattered ever so slightly. And this scattering event would leave a unique telltale signature on the light itself. It would become polarized. You can think of polarization as a faint orientation, a subtle grain imprinted onto the fabric of light. Imagine sunlight reflecting off the surface of a lake. Much of that reflected glare is horizontally polarized, which is why polarized sunglasses designed to block light with that specific orientation can cut right through it. In the same way, the free electrons of the reionization era would have acted like a cosmic polarizing filter for the CMB. They would have scattered a tiny fraction of its photons, imparting a large-scale polarization signal onto the microwave sky. Detecting this signal would be the equivalent of finding a water stain on the universe's oldest photograph, a stain that could only have been left by the waters of reionization. The magnitude of this polarization would tell us just how much of the CMB light had to traverse that electrified plasma. It would in effect measure the duration and the depth of the reionization epoch. It was a signal of almost unimaginable subtlety, a whisper buried within a whisper. To hear it, we would need a new kind of cosmic ear. Enter a satellite named WMAP, the Wilkinson Microwave Anisotropy Probe. Launched in 2001, its singular mission was to create the most detailed full-sky map of the cosmic microwave background ever produced. For years, it orbited in the cold, stable darkness a million miles from Earth, patiently absorbing the faint microwave hiss left over from the dawn of time. Its primary goal was to measure the tiny temperature fluctuations in the CMB with unprecedented accuracy, revealing the seeds of cosmic structure. But its secondary, and for our story, most critical mission was to search for that faint, large-scale polarization. The science community held its breath. If WMAP found nothing, our entire model of what happened after the Dark Ages might be wrong. If it found the signal, it would be the first definitive all-sky proof that reionization had happened, and it would provide our very first timestamp for the event. In 2003, the results came in, and they were a bombshell. The signal was there, faint but unmistakable. WMAP had detected the polarization signature of reionization. It was a moment of profound revelation, a tectonic shift from inference to observation. The fog had lifted, and now we had the proof etched onto the fabric of creation. The universe had indeed passed through a second great transformation, a violent adolescence where the light of the first objects fundamentally re-engineered the cosmic environment. But the WMAP data did more than just confirm the event. It gave us a timeline, and that timeline was shocking. The signal was stronger than most models had predicted, suggesting that a significant fraction of the universe was already reionized very, very early. WMAP's initial data placed the onset of reionization at a mere 200 million years after the Big Bang, barely a cosmic heartbeat, after the very first stars were thought to have formed. This was a puzzle. Could those small primitive galaxies seen by Hubble have possibly formed so quickly and produced enough radiation to have such a dramatic impact so early? The timeline felt compressed, the event too sudden. The data ignited a firestorm of debate. It seemed we had solved one mystery only to create a dozen more. The detective story had its proof, but the timeline was throwing all the suspect profiles into disarray. Science, however, is a relentless process of refinement. WMAP had opened the door, but we needed a more sensitive instrument to map the details of the room inside. That instrument was Planck, a European Space Agency mission launched in 2009. If WMAP was a standard definition television for the early universe, Planck was a state-of-the-art high-definition 4K display. It was designed to measure both the temperature and the polarization of the CMB, with a sensitivity and resolution that dwarfed its predecessor. For 4 years, Planck scanned the heavens, its instruments cooled to within 1/10 of a degree of absolute zero, charting the ancient light with breathtaking fidelity. And its refined measurements of the reionization signal would once again rewrite the timeline. Planck's data, released in a series of papers starting in 2013, confirmed WMAP's discovery of the polarization signal, cementing it as a pillar of modern cosmology. But it also dialed back the clock. The signal was not quite as strong as WMAP had initially measured. Planck's more precise analysis showed that reionization was a more protracted and complex affair. It didn't happen in one sudden early burst. Instead, it was a gradual dawn that likely began later, perhaps around 400 million years after the Big Bang, with its midpoint the moment the universe was about 50% transparent, occurring much later, around 700 to 800 million years after the beginning. The process finally concluded with the last vestiges of the fog burning away when the universe was nearly 1 billion years old. This new, more nuanced timeline was a revelation. It eased the tension created by the WMAP results, providing a more plausible window for the first galaxies to form mature and collectively achieve their universe-altering work. And with this, the two great lines of evidence finally converged. On one hand, we had Hubble's deep field images showing us the countless faint star-forming galaxies that existed during this precise window of time. These were the foot soldiers of Reionization. On the other hand, we had Planck's exquisitely precise measurement of the CMB polarization, providing a global, statistically robust timeline for when their work was done. The evidence was in. The case file was open. We had the culprits, and we had the time frame of the crime. But now the central question of the investigation shifted. The mystery was no longer if it happened, or even when it happened. The mystery was how. Were those innumerable tiny galaxies seen by Hubble truly the sole agents of this cosmic transformation? Or was there another more powerful force at play? This convergence of data sparked one of the most intense and fascinating debates in modern astrophysics, a clash of cosmological theories that continues to this day. It is the battle of the Reionizers stars versus quasars. In one camp, we have the proponents of a kind of democratic revolution. They argue that Reionization was a grassroots effort accomplished by the collective distributed power of billions of small infant galaxies. Each one on its own was relatively insignificant, a tiny pinprick of light in the overwhelming darkness. But together their combined ultraviolet radiation was a relentless rising tide. According to this model, each galaxy first carved out a small local bubble of transparency in the thick fog of neutral hydrogen around it. These bubbles, like expanding pockets of air in a block of Swiss cheese, grew and grew over hundreds of millions of years. Eventually they began to overlap, merging into larger and larger superbubbles, until finally the last walls of neutral gas between them collapsed, and the entire universe became a single interconnected transparent volume. It's a story of countless small efforts achieving a monumental outcome. But there is another camp, one that argues for a more aristocratic top-down model. They point to a far more ferocious, more luminous and far rarer beast, the quasar. Quasars are the catastrophically bright cores of the most active early galaxies, powered not just by stars, but by supermassive black holes feeding on incomprehensible amounts of gas and dust. As this matter spirals towards the event horizon, it is superheated into a swirling accretion disk that can outshine its entire host galaxy by a factor of thousands. A single quasar is not a gentle lamp. It is a celestial blowtorch, a lighthouse in the cosmic fog capable of blasting out torrents of high-energy radiation and ionizing vast regions of space all on its own. The proponents of this model argue that while the small galaxies did their part, the heavy lifting of reionization was done by these rare titanic engines of light. A few hundred powerful quasars, they suggest, could have done the work of millions of dwarf galaxies and done it much more efficiently. The problem, however, is one of scarcity. While we have found quasars existing in the Reionization era, they appear to be exceptionally rare. Were there enough of them scattered across the early cosmos to truly be the primary drivers of this global transformation? And so the stage is set for the next chapter of our investigation. We have the timeline from Planck, a firm cosmic boundary. We have the two primary suspects from Hubble and other deep surveys, the countless faint galaxies, and the rare, brilliant quasars. Each suspect has a motive and a means, but neither case is airtight. To solve this mystery, to finally determine who turned on the lights in the universe, we need more than just photographs and echoes. We need to conduct an intergalactic interrogation. We need to capture the light from these first galaxies and quasars with such clarity that we can analyze its chemical fingerprint to measure exactly how much ionizing radiation they were leaking into the void around them. We need to map the fading edges of the cosmic fog itself to see if it was eroded slowly by a billion small sources or blasted away in giant clearings by a few powerful ones. For that we would need a new eye on the sky, a machine so powerful it could make even Hubble look nearsighted. a telescope capable of not just seeing the dawn but of dissecting its light one photon at a time. The investigation was far from over. In fact, it was just about to get interesting, and so the picture was complete, or so it seemed. The telltale signature of a universe transformed from an opaque fog of neutral hydrogen into the transparent star-filled cosmos we know was finally etched into our data. The discovery of the Gunn-Peterson trough and the precise measurements of the cosmic microwave background had provided the bookends to this epic tale. Reionization was no longer a theory. It was a recorded historical event, a definitive chapter in the cosmic story. For a brief shining moment there was a sense of profound closure, a feeling that one of the grandest puzzles of our origins had been solved. But science is a relentless interrogator. The answer to one question almost invariably gives birth to a dozen more, each more complex and demanding than the last. As the initial wave of celebration subsided, astronomers turned from the what to the how. They began the meticulous, painstaking work of cosmic accounting. They knew the cost of victory over the darkness. They could calculate with unnerving precision the colossal amount of high-energy ultraviolet radiation required to strip the electron from every single hydrogen atom across billions of light-years of space. It was an energy bill of truly astronomical proportions. The next logical step, then, was to balance the books to survey the young universe and tally up all the sources of that light. And it was here in this simple act of celestial bookkeeping that a terrifying ghost-like discrepancy began to emerge. A shadow fell across the triumphant discovery. When we peered back with our most powerful telescopes like the Hubble into that nascent epoch, we found the suspects we expected. We saw the faint primordial glow of the first infant galaxies struggling to assemble themselves from the chaos of the cosmic dawn. We also detected the brilliant violet beacons of the first supermassive black holes known as quasars, which acted as celestial blowtorches spewing out immense quantities of ionizing radiation as they devoured surrounding matter. These were the engines of change, the lighthouses that were supposed to have burned away the primordial fog. The problem was when we counted them all up, when we carefully measured their brightness and calculated their total output, the numbers didn't work, not even close. The quasars, for all their spectacular brilliance, were far too rare. In that early period, they were like isolated searchlights in a planetary-scale blackout, powerful but vastly outnumbered by the darkness. They could have certainly ionized their local neighborhoods, carving out significant bubbles of transparency, but they simply didn't have the reach to reionize the entire intergalactic medium on their own. The primary responsibility, therefore, had to fall upon the shoulders of the first generations of stars nestled within those fledgling galaxies. These were the foot soldiers of the Reionization army, the countless tiny torches meant to collectively achieve what the few giant bonfires of the quasars could not. Yet as our telescopes strained to their absolute limits, the galaxies they could detect were themselves too few and too faint. A chilling realization began to creep into the calculations, a deficit so large it became known as the photon underproduction crisis. It was as if we had discovered evidence of a planet-wide forest fire, but could only find a handful of scattered campfires to explain it. We were missing at least 80% of the required radiation. The cosmic budget was profoundly, stubbornly unbalanced. The universe's ledger was awash in red ink, showing an immense expenditure of energy, with no discernible source of income. This wasn't a minor rounding error. It was a fundamental flaw in our understanding. It meant that either our census of the early universe was catastrophically incomplete, or the first stars and galaxies behaved in ways we had completely failed to predict. The grand narrative of reionization, which we thought we had finally deciphered, was suddenly riddled with a massive plot hole. This crisis forced us to re-examine our most basic assumptions. It sent theorists and observers scrambling back to their drawing boards, questioning every part of the equation. Perhaps the problem wasn't with the number of sources, but with the sources themselves. What if those first stars, the pristine population 3 stars forged from pure hydrogen and helium, were fundamentally different beasts than the stars we see today? Theory suggested they could have been colossal hundreds of times the mass of our Sun. Such leviathans would have burned hotter, brighter, and lived far shorter, more violent lives. Could these short-lived superluminous stars have produced a flood of ionizing photons far greater than our models based on modern stars had predicted? It was a tantalizing idea, But these first-generation stars have remained stubbornly elusive ghosts in the cosmic machine. They would have all died out long ago, leaving behind only the faintest chemical traces in the generations that followed. Relying on them to solve the budget crisis felt like invoking a phantom army. A second, more promising avenue of investigation focused not on the light's creation but on its escape. A galaxy, especially a young one, is not a clean, empty vessel. It is a chaotic, messy construction site choked with vast clouds of the very same neutral hydrogen gas that the starlight is meant to destroy. It is also filled with dust, the soot forged in the hearts of dying stars. For a galaxy to contribute to the reionization of the universe beyond its borders, its ionizing photons must first fight their way out of their own home. This critical variable is known as the escape fraction, the percentage of high-energy photons that successfully break free from the gravitational and gaseous clutches of their host galaxy and journey out into the vast emptiness of intergalactic space. Our initial models had assumed a relatively high escape fraction. We pictured these early galaxies as somewhat porous structures leaking light into the cosmos. But what if that assumption was wrong? What if these first galactic systems were more like impenetrable fortresses? The immense gravitational pull of their dark matter, halos, would have held onto gas with ferocious tenacity. The very star formation that produced the light would have also churned up the galactic medium into a thick, turbulent shroud. In this scenario, a galaxy could be blazing with internal light, a furnace of young, hot stars, yet from the outside it would appear dim. Its most powerful ionizing radiation would be absorbed almost instantly by the gas clouds in its own disk. Its power turned inward, reionizing its own local environment, but contributing almost nothing to the grand cosmic scale project. This concept completely reframed the problem. The photon underproduction crisis might not be a crisis of production at all, but a crisis of delivery. The factories could be working overtime churning out photons at an incredible rate, but if the cosmic shipping and logistics network was failing, the goods would never reach their destination. If the escape fraction was on average very low, say only 5 or 10%, then we would need vastly more galaxies than we had previously estimated to get the job done. The shortfall in our census suddenly looked even more severe. We weren't just missing a few campfires, we were missing entire hidden cities, all burning furiously but shrouded from our view. This led to a profound shift in how we visualized the entire Reionization Epoch. The old idea of a simple uniform event like a global sunrise happening everywhere at once was shattered. It could not have been a smooth monolithic transition. Instead, the process must have been incredibly complex, messy, and geographically patchy. Reionization wouldn't have been a single coordinated event, but a long drawn-out guerrilla war waged by light against darkness, fought galaxy by galaxy, cluster by cluster. Imagine you are floating in that primordial ocean of neutral hydrogen. In the beginning, the blackness is absolute, extending in every direction. Then in the distance, a point of light ignites. A single brave galaxy is switched on. Its ultraviolet radiation begins to push outwards, not like a wave, but like a bubble being inflated. Inside this bubble, the hydrogen is ionized transparent. Outside, the universe remains opaque. This is an island of clarity in an infinite sea of fog. Soon, another galaxy, millions of light years away, ignites its own engines, inflating its own bubble of influence. For millennia, these bubbles would grow in isolation, their expansion, driven by the furious light pouring from their centers. The spaces between them, the vast intergalactic voids, would remain dark and neutral for a very long time. An observer in one bubble would have no knowledge of the existence of the other. As time marches on, more and more galaxies switch on, each creating its own pocket of transparency. The cosmic structure begins to resemble a kind of Swiss cheese, with holes of ionized plasma growing inside a still dominant medium of neutral gas. The next crucial phase is overlap. Eventually, two expanding bubbles born from neighboring galaxies or clusters would touch. Their boundaries would merge, creating a larger, irregularly shaped region of clarity. This process would continue for hundreds of millions of years. It would be a sprawling, chaotic campaign of annexation and consolidation. Dense, gas-rich regions of the cosmic web would have been the last to fall their high concentration of neutral atoms, requiring an overwhelming barrage of photons to finally ionize. These would have been the final stubborn pockets of resistance holding out against the encroaching light long after the less dense voids had been cleared. The end of the Dark Ages, therefore, was not a singular moment. It was a rolling, percolating process of transformation, where the last vestiges of the primordial fog were not burned away until these countless individual bubbles of ionization had finally all merged into one single universe-spanning ocean of transparency. This patchy reionization model solved many of the conceptual problems, but it deepened the observational challenge. It confirmed that our census of the early universe had to be missing something fundamental. To make this model work, the cosmos had to be teeming with sources we couldn't see. The burden of proof fell upon a vast hidden population of incredibly small faint galaxies. These would not be the majestic spirals we see today, but tiny, scrappy dwarf galaxies, perhaps thousands of times less massive than our own Milky Way. Individually, their light would be insignificant, a mere flicker in the gloom. But if they numbered in the trillions, their combined effort could just possibly account for the missing 80% of the light. They would be the worker bees of the cosmos, the unsung heroes who collectively accomplished the Herculean task of reionizing the universe. The Hubble Space Telescope, for all its power, was simply not designed to find such phantoms. It could spot the brighter, more established cities of the early universe, but these hypothetical galactic villages and hamlets were below its detection threshold, their faint light lost in the noise of deep space. Our cosmic accounting was flawed because we were only counting the millionaires, while the entire economy was actually being driven by the combined wealth of a billion uncounted citizens. Finding them would require a new kind of observatory, an instrument with unprecedented sensitivity and the ability to capture the faint red-shifted infrared light from these most distant and ancient of structures. And so the triumph of confirming reionization had led directly to a far deeper and more formidable mystery. We had found the crime scene, but the majority of the culprits remained at large, hidden in the shadows of cosmic history. The simple picture of a dawning universe had been replaced by a complex tapestry of overlapping bubbles driven by a ghost population of galaxies we had yet to prove even existed. The beautiful, clean theory had crashed against the messy, complicated, and far more interesting reality. To solve the photon crisis and truly understand how the lights came on, we had to move beyond simply knowing that it happened. We needed to map the process to witness the bubbles growing and merging to conduct a true census of the cosmic dawn. We needed to find the missing light. That quest would demand a new generation of technology, a machine capable of staring into the abyss and seeing the unseeable, a golden eye designed to capture the faint residual heat of creation itself. And so we were left adrift in a profound cosmic paradox. The numbers simply refused to align. Our universe, fully illuminated and transparent today, demanded a price be paid in photons, a staggering quantity of high-energy light needed to strip the electrons from every atom of hydrogen in the vast, cold darkness. Yet when we counted our known sources, our brilliant quasars, and the brightest, most heroic galaxies of that ancient dawn, their combined output fell impossibly short. It was a budget crisis on a cosmic scale, a story with a brilliant shining end, but a missing crucial chapter, explaining where all that light had come from. The fog had cleared, we knew that for a fact. But the beacons powerful enough to clear it remained stubbornly hidden, lost in the deepest recesses of time. We were staring at an answered prayer with no memory of who had spoken the words. For decades, this missing light haunted cosmology, a ghost in the grand machine of the universe. To solve it, we couldn't just build a better telescope. We had to build a different kind of eye. We had to build a time machine. We called it the James Webb Space Telescope. It is perhaps the most ambitious instrument humanity has ever conceived, a breathtaking sculpture of gold-plated beryllium, folded like celestial origami into the tip of a rocket. Its destination was not orbit around the Earth, but a lonely silent point 1 million miles away, a place of gravitational balance called a Lagrange point. Here, shielded from the blinding glare of our own planet and sun by a 5-layered shield, the size of a tennis court, its gaze could cool to just a few degrees above absolute zero. This extreme cold was not an engineering vanity, it was an absolute necessity. For Webb was not designed to see the universe as we do in the familiar visible light of our star. Its purpose was to see in the infrared, to hunt for light that has been travelling for so long across such an expanding fabric of space-time that its very wavelength has been stretched red-shifted from brilliant ultraviolet and visible light into the subtle warmth of infrared radiation. It was built to see the invisible. It was designed from its very first blueprint to find the missing chapter of our story, to stare directly into the heart of the cosmic dark ages and witness for the first time the flicker of the universe's first dawn. The anticipation was a palpable thing, a held breath felt in control rooms and university departments across the globe. Decades of work, the careers of thousands of scientists and engineers, all hinged on a flawless deployment a million miles from any helping hand. And then it began to work. The mirrors unfolded, aligning with a precision finer than a fraction of a human hair. The instruments cooled to their operational temperatures, and we turned this golden eye towards a patch of sky that appeared to every other telescope almost completely empty, a tiny dark window in the constellation of Volans. We simply opened the shutter and let the ancient light pour in, gathering photons that had been journeying towards us since before the Earth itself had even formed. The first images that returned were a quiet revolution, a whisper that would soon become a roar. We saw the familiar tapestry of the Hubble deep fields, but rendered with an impossible clarity galaxies spiraling with newfound detail, their structures sharp and vibrant. Yet this was merely the foreground. The true prize lay deeper. It lay in the background, behind the familiar and the faintest reddest specks of light imaginable. As astronomers pushed Webb to its absolute limits, staring at that same patch of sky for hundreds of hours, the true nature of the early cosmos began to reveal itself. And it was nothing like we had expected. The prevailing theory, born from the limitations of our older telescopes, suggested that Reionization was a top-down affair, driven by the rare monolithic titans of the early universe. We expected to find a few massive galaxies blazing with the light of a billion suns, acting as colossal lighthouses, carving out huge bubbles of transparency in the hydrogen fog. What Webb showed us was the precise opposite. The titans were there, yes, but they were vastly outnumbered. As the image resolved, a hidden population exploded into view. The darkness was not empty at all. It was teeming, swarming with an entire ecosystem of faint red compact galaxies. They were everywhere. For every single bright galaxy we had been able to see before, Webb was now revealing 10, 20, 100 more. These were not the giants of cosmic history. They were the commoners, the humble villagers, the cosmic plankton that formed the base of the entire galactic food chain. And their sheer, overwhelming number changed everything. We were looking at the universe as it was just 300 or 400 million years after the Big Bang, a time when everything was smaller, messier, and more chaotic. These faint galaxies were the building blocks of everything that would come later, the seeds from which giants like our own Milky Way would eventually grow. They were knots of gas and dark matter furiously converting their primordial fuel into the first generations of stars at a rate that seems almost unimaginable today. Inside these tiny crucibles, stars were being born with a ferocious intensity, creating a flood of the very high-energy ultraviolet photons needed for reionization. But this alone wasn't the solution. The photon crisis had never been about a lack of production. We always knew early stars produced this light. The problem was getting that light out of the galaxy where it was born. In a large, mature galaxy like Andromeda, dense clouds of gas and dust absorb nearly all of this ionizing radiation, trapping it within the galactic borders. The light is used up internally, unable to escape and contribute to clearing the intergalactic fog. We had assumed the same would be true for these early systems. This assumption, it turns out, was fundamentally wrong. Webb's instruments, particularly its near-infrared spectrograph or NIRSpec, allowed us to do more than just see these galaxies as faint smudges. We could dissect their light, spreading it into a rainbow to read their chemical composition, their distance, and most importantly, the properties of the gas both inside and around them. The data confirmed their extreme distance, placing them squarely within the Reionization Epoch. But it also revealed something spectacular. These small primordial galaxies were surprisingly porous. They were like cosmic sieves. Because they were so small, their gravitational pull was weaker. The very first massive stars born within them lived fast and died young, exploding as supernovae of unimaginable power. These explosions, occurring one after another in such a compact space, acted like a celestial blowtorch punching holes and channels directly through the galaxy's own gas supply. They were effectively blasting escape routes for their own ionizing light. It was a process of self-sabotage that was for the universe an act of ultimate creation. While a massive galaxy might trap 99% of its ionizing photons, these tiny systems were leaking them like broken lanterns, spilling their transformative light out into the intergalactic medium. Suddenly, the photon budget began to balance. The crisis began to dissolve not with the discovery of some new exotic source of light, but through a radical shift in our understanding of the cosmic ecosystem. The solution to reionization wasn't a few colossal searchlights. It was the combined collective glimmer of 1 trillion flickering candles. Each individual galaxy contributed only a tiny, insignificant bubble of transparency around it. A single one of these systems on its own would have made no difference at all, its small sphere of influence quickly crushed and neutralized by the infinite sea of neutral hydrogen surrounding it. But there were billions of them. Billions upon billions all across the sky, each one pumping out its precious leaking photons. It was a grassroots revolution on a cosmic scale. Their tiny bubbles began to overlap. First 2, then 4, then 12. These small pockets of ionization began to merge, creating larger and more complex ionized regions like tributary streams flowing together to form a river. The process wasn't uniform, it was patchy and chaotic. Some regions of the universe dense with these fledgling galaxies would have cleared much earlier than others, creating a complex Swiss cheese-like structure of transparent voids within the opaque fog. What Webb allows us to see is this process in action. By observing different deep fields, we can capture snapshots of this era at slightly different times, witnessing the growth of these ionized bubbles. We can now map the topology of reionization, charting the advancing frontier of light as it wages its million-year war against the darkness. This discovery fundamentally rewrites the story of cosmic evolution. It tells us that the universe was not built by kings and giants alone. It was built from the bottom up by the tireless collective effort of the countless and the small. The faint galaxies Webb has unveiled are our own most distant ancestors. Within these chaotic, leaky, furiously star-forming systems, the first heavy elements were forged. The chemical enrichment of the cosmos began here. The seeds of the majestic spiral galaxies that decorate our modern universe were planted in these humble, unassuming nurseries. They were not just the agents of reionization, they were the authors of the entire cosmic story to come. They cleared the stage, set the scene, and provided the raw materials for everything that followed for our galaxy, for our sun, and ultimately for us. The resolution to the photon crisis is therefore more elegant and far more profound than we could have hoped. The missing light wasn't hiding in some exotic object. It was hiding in plain sight, distributed amongst a population of galaxies so numerous and so faint that they were simply below the threshold of our vision until now. The Webb telescope has finally given us the eyes to see them, to count them, and to understand their collective power. It has shown us that to reionize an entire universe, you don't necessarily need a few suns. You just need enough fireflies all blinking on at once. We have found the source of the light. We have witnessed the moment the fog began to lift. And as these bubbles of transparency grew and merged, swallowing up the last remaining islands of neutral gas, they set in motion the final act of this grand transformation, forging the vast, interconnected cosmic web that would come to define the structure of the universe for the next 13 billion years. The lights were on, the darkness was in full retreat, and the modern cosmos was about to be born. And so our long voyage through the cosmic dawn reaches its shore. We have journeyed back across 13 billion years of expanding space, peering through the telescopic abyss to a time before time as we know it, a period of profound and utter blackness. We began with a deceptively simple question, a cosmic paradox that haunted astronomers for decades. How did a universe born in a flash of incandescent plasma fall into a chilling, starless dark, and then somehow learn to shine again? The answer, as we have discovered, was not a single event, but a sprawling globe-spanning saga of cosmic rebirth. It was the epoch of reionization, a dramatic, chaotic, and utterly transformative chapter in the universe's biography. Our investigation has been a masterclass in cosmic forensics. We could not simply point a telescope and watch this ancient sunrise happen. Instead, we have been detectives gathering subtle, scattered clues left behind at the scene of the crime. We have analysed the ghostly shadows in the light of the most distant quasars, those spectral fingerprints of neutral hydrogen that told us the fog was once thick and pervasive. We have examined the faint polarized glow of the cosmic microwave background, searching for the telltale signs of scattered photons, the last whisper of an encounter with newly freed electrons which hinted at when the process might have begun. And we have stared with an almost painful intensity into the deepest fields of space, hunting for the culprits themselves, those faint red-shifted smudges of light that were the very first galaxies. Each clue on its own was a tantalizing but incomplete fragment. The quasar spectra gave us a snapshot of the final moments, the clearing of the last cosmic mists. The CMB polarization offered a blurry, smeared-out average of the entire half-billion-year-long event. The deep fields from Hubble and Webb showed us the potential engines of this transformation, but not the transformation in progress. It was like trying to understand a revolution by studying a single newspaper from its final day, an old faded photograph of the crowd and a list of the architects. We had the ending, a vague timeline and the key players, but the revolution itself, the messy dynamic and intricate process of light battling darkness across millions of light years, remained shrouded. Yet by piecing these disparate threads together, a breathtaking picture has begun to emerge. We now understand that reionization was not a monolithic instantaneous flip of a switch. It was a patchy, complex and violent process. It began in the densest knots of the cosmic web, where gravity had been ruthlessly efficient, pulling together the first collapsing clouds of gas. Within these dark matter halos, the universe forged its first engines of change, population 3 stars. These were not stars like our Sun. They were monsters hundreds of times more massive, burning with a ferocious blue-white intensity for a mere million years before exploding in supernovae that shook the fabric of the early cosmos. These primordial stars were the first torches in the dark, their ultraviolet radiation a celestial blowtorch of unimaginable power blasted into the surrounding neutral hydrogen, carving out the first bubbles of transparency. These were isolated pockets of clarity in an otherwise opaque universe, ionized oases in a desert of primordial fog. As these first stars died, their gravitational remnants seeded the formation of the first protogalaxies, which ignited with subsequent generations of stars, creating even larger, more persistent bubbles of ionized plasma. For hundreds of millions of years, this was the state of the cosmos, a frothing, bubbling cauldron where islands of light fought to expand and merge against an ocean of darkness. We have come to realize that this was not merely a story about light. It was a story about the birth of complexity itself. The very same ultraviolet radiation that was clearing the fog was also profoundly reshaping the universe's ability to create. Before reionization, gravity was the only major force orchestrating cosmic structure. But the intense radiation from early stars and quasars introduced a new powerful feedback mechanism. This light and heat could evaporate smaller gas clouds, preventing them from forming new dwarf galaxies and effectively sterilizing vast regions of space. At the same time, the shockwaves from the first supernovae compressed gas in other regions, triggering new bursts of star formation. Reionization, therefore, was the great sculptor of the galaxies we see today. It determined which galaxies could grow and which would be snuffed out before they truly began. It helped to carve the vast empty voids in the cosmos and to define the glittering filaments of the cosmic web. It was the crucible that forged the hierarchy of cosmic structure, setting the stage for the emergence of massive spiral and elliptical galaxies from an initially humble population of faint blue dwarfs. When you look at an image of a majestic galaxy like Andromeda, you're seeing a direct descendant of this violent, light-drenched era. Its size, its shape, and its very existence are predicated on the events that unfolded during those first billion years. The universe didn't just become transparent, it became interesting. It transitioned from a simple, predictable state of hydrogen and helium to a complex dynamic ecosystem of stars, galaxies, and intergalactic gas capable of cooking up all the heavier elements that make planets and ultimately us possible. This new understanding is a monumental achievement, a testament to human curiosity and ingenuity. But it is also in many ways just the prologue. Our current picture of reionization is like a charcoal sketch, capturing the broad outlines of the event but lacking the fine detail, the colour, the texture of the reality. We have inferred the existence of the bubbles. We have modelled their growth on supercomputers. We have glimpsed their indirect effects. but we have never truly seen them. We have never been able to create a direct map of that primordial fog to watch, frame by frame, as those first pockets of light expanded and merged into the transparent universe we inhabit today. The grand challenge of 21st century cosmology is to move beyond the sketch and paint the full masterpiece. To do that, we are building a new generation of eyes on the universe observatories of such scale and ambition that they dwarf everything that has come before. On the high dry plains of the Atacama Desert and atop the sacred mountain of Mauna Kea, colossal structures are taking shape. These are the new optical giants, the extremely large telescope, the 30-metre telescope, and the giant Magellan telescope. With mirrors stretching up to 40 metres across, these behemoths will gather light with a sensitivity that borders on science fiction. They will be our time-travelling spectroscopes capable of capturing the faint red-shifted light from individual galaxies deep within the epoch of reionization. They won't just see these galaxies as faint smudges, they will dissect their light photon by photon. They will be able to measure the chemical composition of these infant star systems to gauge the intensity and nature of their ionizing radiation and to map the outflows of gas being driven by their first supernovae. With these telescopes, we will move from cataloguing the likely sources of reionization to performing detailed autopsies on them. We will finally be able to answer one of the most pressing questions. Was it countless tiny dwarf galaxies, each punching small holes in the fog? Or was it a smaller number of larger, more brilliant galaxies that did the heavy lifting? These ground-based giants working in concert with the James Webb Space Telescope in orbit will give us the census of the light bringers, the complete cast of characters for our cosmic drama. But to truly understand the story, we need to see not just the actors but the stage itself. We need to see the fog, and for that we cannot use visible or infrared light because the fog itself by its very nature absorbs it. To see the darkness we need an entirely new kind of sense. We must listen for a whisper, a faint ghostly hum that has been travelling across the universe for over 13 billion years. This is the sound of hydrogen itself. It is the 21 centimetre signal, an incredibly subtle radio wave emitted when the electron in a neutral hydrogen atom spontaneously flips its spin relative to the proton it orbits. In the dense, dark fog of the early universe, trillions upon trillions of hydrogen atoms were constantly making this tiny transition, broadcasting a faint collective radio signal in all directions. As the universe expanded, this signal was stretched redshifted from its original 21 centimetre wavelength to meters-long radio waves by the time it reaches Earth today. For decades, detecting this signal from the epoch of reionization was considered an impossible dream. It is unimaginably faint, a signal billions of times weaker than the radio noise from our own Milky Way galaxy, let alone the cacophony of human-made interference from FM radio stations, television broadcasts and satellites. Picking out this cosmological whisper from that roar of foreground noise has been compared to trying to hear a single bee buzzing in the middle of a hurricane. But impossibility is merely a challenge that human ingenuity has not yet overcome. And across the world we are building the ears to hear that buzz. In the quiet, radio-protected zones of the Australian outback and the South African Karoo, a revolutionary project is underway, the Square Kilometre Array, or SKA. This is not a single telescope, but a continental-scale instrument and array that will eventually link hundreds of thousands of individual antennas together, creating a collecting area of 1 square kilometre. The low-frequency portion of this array, SKA-low, in Australia is specifically designed for one primary purpose: to map the hydrogen fog during the epoch of reionization. The sheer scale of the undertaking is difficult to comprehend. Imagine an array of 131,000 antennas resembling metallic Christmas trees scattered across 65 kilometres of desert, all digitally connected and synchronized with atomic clock precision. The data flowing from this array will be astronomical, exceeding the entire current global internet traffic. Processing it will require some of the most powerful supercomputers ever constructed. The result of this monumental effort will be nothing less than a three-dimensional movie of the universe waking up. The SKA will not just detect the 21 centimetre signal, it will use its vast array to achieve what is known as tomography. By tuning the receivers to slightly different radio frequencies, astronomers can effectively tune into different cosmic distances corresponding to different moments in time. It's like adjusting the focus on a microscope, allowing us to see one slice of cosmic history at a time. One frequency will show us a map of the neutral hydrogen fog at say 500 million years after the Big Bang, when the universe was almost entirely opaque. A slightly different frequency will reveal the universe 50 million years later, where the first ionized bubbles carved by the first stars appear as dark holes in the hydrogen map. As we scan through the frequencies, we will be able to watch for the very first time as those bubbles grow. We will see them expand from their galactic birthplaces, elongating along the filaments of the cosmic web. We will watch them merge with their neighbours, creating ever larger regions of transparency. We will witness the final dramatic moment when the last pockets of neutral gas are burned away and the intergalactic medium becomes the fully ionized, transparent state we know today. We will be able to measure the size, shape and distribution of these bubbles throughout the entire epoch, providing a direct, unambiguous record of how Reionization unfolded across cosmic time. This will be the ultimate synergy in observational cosmology. The James Webb Space Telescope will show us the pinpoint sources of light the candles being lit in the dark. The giant ground-based telescopes will tell us exactly how bright and hot those candles were, and the square-kilometre array will show us the shape of the darkness as it was pushed back by that candlelight. It is the complete picture, the story told from every perspective. We will no longer have to infer to guess to model. We will know. We will have a direct observational history of how our universe became a realm of light and structure. The quest to understand our cosmic origins has always driven us to build bigger, to see farther, to imagine more boldly. From Galileo's first spyglass to the Hubble Space Telescope, each new window on the universe has revealed a cosmos far more wondrous and complex than we had ever conceived. We now stand at the threshold of the next great leap. We are on the verge of directly witnessing the second most important event in the history of the universe after the Big Bang itself. We are about to watch the cosmic sunrise. The great silent darkness that reigned for hundreds of millions of years is finally about to give up its secrets. The story that began with a faint uniform glow plunged into an eon of blackness and then erupted into a universe of brilliant structured galaxies is about to have its most pivotal chapter read aloud. And for the first time in human history, we will have a front row seat.